Yeah, before starting this chapter, I will just start with an overview how to name let's say, the different compounds in organic chemistry. If you watched the previous video, you know that organic chemistry deals with all the compounds that contain the carbon that covalently bond with some common elements like hydrogen, nitrogen, oxygen, and other elements, of course, fluorine and so on. So how do we name them? When we have one carbon group, so it's a meth and then something. If it's like a group that is related to a much more longer hydrocarbon chain, then it's methyl. Otherwise, if it's just the group itself, CH4, because you know the carbon can bond to four different hydrogens, so it's CH4, then it's methane. Then when we go further, so if we the more we have carbon in the molecule, then the name will change, of course. So the name depends on the number of carbon atoms in the molecule. So if we have two carbon atoms, so two groups, let's say, then it's eth something, so ethyl in this case. Then propyl, if we have three carbons, four carbons is butyl. Watch the but. So this termination changes depending on the class, and I will explain in a while what class means. And this prefix remains. So meth, eth, prop, but, and so on. So if we have five carbons, pentyl, six carbons, hexyl, heptyl, octyl, and so on. Then we have the dec and nano, and so it's up to here. It's what we need to know. And now I will focus on this slide. So I want to explain what a functional group is and why it's important. So a functional group is what characterizes a compound from another in the organic chemistry and what puts it in a certain class. The elements that, or the compounds that belong to the same class and therefore have the same functional group, they behave in a particular way. So they exhibit a specific chemical behavior and react with some reagents in the same way. Now, of course, the longer the chain is, the reactivity may change a bit, but like the reagents remain the same. We expect the same effect and we expect the same compound to be formed. So for example, if we expect an alcohol and a carboxylic acid, these are two different groups. No matter how many number of carbon atoms or carbon groups are in those chains, of course, the product itself will differ, but the group to which this product belong remains the same. So if we have, for example, an alcohol and carboxylic acid, then we will have an ester, and so on. So this is what characterizes a specific group. It's the functional group that it has, and this functional groups normally exhibit a polar character, which means it can be soluble in water, and molecules can have more than one functional group. So why does it exhibit a polar character? Because those functional groups are usually containing an oxygen or a nitrogen. And if you remember, in the electronegativity table, the most three electronegative elements were the F, O, and N, so the fun. And they exhibit a specific polar character. So the OH bond is polar because oxygen is electronegative, and it tends to have a delta minus charge and the hydrogen delta plus charge, and they form hydrogen bridges with another, let's say, nearby compound. So they can form hydrogen bridges with water, which are also made of H and O bonds and polar bonds, and that's why they are soluble in water. And the same for the amino group, the NH2, because nitrogen is also a polar element. So like oxygen, it's electronegative, and this bond between N and H is also polar, so it is soluble in water. Now, when we have, like for example, in this compound, two different groups, It's possible, but the class here is a combination of both. So we have this amine, which is a functional group, and we have this here. This is a carboxylic group or carboxy group, which is C double bond O and OH. And this is a specific functional group for carboxylic acids. Here we have two different functional groups. So this is a carboxylic acid, but at the same time it's an amine. So we call it an amino acid. And you know, an amino acid is a protein, so they are like in our body. They are made of two different functional groups. And here we don't care. It can be just a hydrocarbon chain or some aromats in it. Anything can be here. What we care about is these two functional groups that really characterize this molecule and show us that this is an amino acid. And it's soluble in water. Of course, this also plays a role because this chain is normally nonpolar, so the CH bond is nonpolar, and it has this nonpolar character, so not soluble in water, but soluble in nonpolar substances like oil. Whereas these functional groups are soluble in water because they are polar. So it has some mixture of soluble and non-soluble parts. And it has an acidic character because this is a carboxylic acid is a weak acid. And the amine group is alkaline. Is an alkaline, so has an alkaline character. So we call it amphiolic. Amphiolic, which means it has two pKa values. You know, the pKa that determines how strong an acid is, let's say. So depending on the pKa, we know that a carboxylic acid is not a strong acid, it's a weak acid. But the other, it has also another pKa depending on because this is here is shows an alkaline character. So let me explain briefly why it's alkaline, the amine group, because you know the nitrogen belongs to the fifth group. I want to make it like this, and it has this lone pair. So it can bond to three different compounds. It can form three different bonds. Here is just some radical. So this chain here, whatever it is, we just call it R if we don't care about it, which means radical. And here there is the H, another H, you know, it's like 2H. So these are the three bonds. Now, in some cases, this is made of two different electrons, so it's a lone pair. This one can break and can be extended, like given one electron remains here and the other is just bonding to forming a bond, so giving one electron to a proton. A proton means a hydrogen that lost its electron. So this is a hydrogen normally, it has the proton in the middle and one electron. When it loses its electron, it becomes just one proton, so we call it H+, which is a proton. So H+ without an electron can like get this, can bond, let's say, because it's a proton, so it's positively charged, the proton is exposed, and can bond to this lone pair in a way so it can capture this H+. And when a substance captures H+ in the water, it means we originally had some water molecule, yeah? And this H was just released without its electron. So this electron remained, and the H was released alone. And here now we have an OH minus that remains. So the concentration of OH minus in water has increased because of this compound NH2, because it's bonding to H+. And the definition of a base is either something that can, it is a substance that can favor the concentration of OH minus in water. So when it releases OH minus, so if we have, for example, a base like sodium hydroxide, when the bond breaks in water, we get sodium and hydroxide, OH minus, which means the concentration of OH minus is increased in water. That's great. This is a base, and this is very clear. But when we have a compound like NH2, the amine group, when it bonds to, when it attracts one H also, so of course amine is bonding to something, it can be H, like NH3, or it can be a radical, like here in this case, so an amine. When it capture one more H, so it becomes H plus, let's say, and H3 plus. This means that the water molecule was broken and OH minus was released. So it's also a base because it's still favoring the concentration or increasing the concentration of the hydroxide concentration in water, of the hydroxide ion. So this is why it has this alkaline character, and here it has a acidic character. This is just a side note so that understand what this slide, let's say. Okay, now let's continue and briefly see the different functional groups of the different classes in organic chemistry. So we can have an alkane, which is when we only have single bonds everywhere and no functional groups, so only hydrocarbon chain. This is called an alkane. In this case, if you remember, we said bute is 4 carbons, bute. Here we have 1, 2, 3, 4 carbon groups. So it's a butane. This is the termination. That's why it's called alkane. Then the first class where we have a functional group is alcohol. Alcohol has the functional group hydroxides. And the termination is then -ol. And the prefix depends on how many carbons we have. So in this case, we have this methyl group because it's just one carbon. And then we have the OH group at the end, and it's called methanol. Now the same compound, if we replace the H with another radical, so another hydrocarbon chain, we get an ether. And here in this case, the functional group is not on the side, but in the middle. So you see we have a methyl group, another methyl group, and the oxygen in the middle. So it's a bit like the alcohol, but we just replace the H with another, like a completely new molecule. It can be methyl or just a longer chain. In this case, we call it, the termination is the whole word, so it's ether, the whole word. Then we have the thiol, and it's the same as alcohol, but instead of oxygen, we have the silicone element. So just the functional group is a side group that is SH. When you see this is a thiol, and we call it ethane thiol. So this is the ethane. It's just a normal ethane, like 2 carbon groups and only single bond. So this is an ethane, and we just add the termination thiol. Up to now, we just considered single bonds. Now, when we start seeing a double bond, then we have a new category, which is called alkene with an E. So if we have 2 carbon groups, then it's an ethene. You see, we have only 2 carbon, one here and one there. So this is ethene. Then if we have a triple bond, the group will be alkyne. So here we can also call it the ethene. We can call it as well. We can call it ethylene. Also, this is a second name that you can see sometimes in the literature. And this one with a triple bond is called ethyne with a Y because alkyne. And the conventional name is acetylene. So just a conventional name. Like frequently you see this name instead of ethyne. Okay, let's continue. Then we have this aldehyde. So we also have now double bonds. We continue with double bonds, but now instead of being between the carbons, we have some functional groups. So this carbon double bond with O is called carbonyl. This one here. C double bond O is called carbonyl, and this carbonyl appears in many different classes. If it's at the end, and of course there should be one more bond, so H in this case would be H, then the category is aldehyde. And the termination is L, like here. So we have 1, 2, 3, 4 carbons. You also count the carbon of the functional group, of course. So this is a carbon here. 2, 3, 4. So it's butanal. Now, when you have this, so you replace the H with a radical. So instead of being at the end, this carbonyl group, now it's in the middle between two hydrocarbons. It becomes a ketone. Ketone. Now this is called a keto. The group, I told you it's a carbonyl. When this carbonyl is characterizing a ketone, so it's like just in the middle, in between two different radicals, therefore it's called a keto. So this is the keto group, the keto functional group, and the full molecule is a ketone. The termination is -one. In this case, it's butanone because it's 1, 2, 3, 4. We have 4 carbons. I will just make it a bit bigger. We have 4 carbons. Oh, okay. We have 4 carbons, and the functional group, which is the carbonyl or the keto, is on the second carbon. We can count 1, 2, 3, 4, or 1, 2, 3, 4 normally. But conventionally, as an agreement, the functional group should have the lower number. So in this case, the functional group is on the third carbon, whereas in this case, the functional group is on the second carbon. So we prefer to have a lower number, so we count from the right instead. Like, why do we care? Because it appears in the name. Now, in the case of 2-butanone, we cannot have like a 3-butanone anyway, because if we so 2-butanone means that the keto group, so the functional group, is on the second carbon. It cannot be on the first because it will become a butanol, right? If it's a side chain. It should be in the middle. So it can be on the second or the third. If it's on the third, we have to count from the left to right so that it has the number 2. 1, 2, 3, 4. And we also get the same. We get 2-butanone. So in the case of butanone, we don't have a 3-butanone or another number. But if we have, for example, another carbon here, so here we don't have an H, we have a CH2, and here at the end we have a CH3. So let's write the H explicitly. So we have a pentanone. Then we count 1, 2, 3, 4, 5, which is not true because we should count from right to left so that it has the lower number. So we have to write like this. 1, 2, 3, 4, 5. In this case, we have a 2-pentanone. Okay, and if the functional group is here in the middle, then we have a 3-pentanone. We cannot have another version because if the functional group is here, we will also have a 2-pentanone because we will start counting from left to right. So this is a short, brief explanation. Okay, let's continue the functional groups. Now, instead of an H, we have an OH. So we have this functional group, C double bond O, OH, and this is a carboxy group. At the end, of course, it's a side group at the end of the chain, and it's called, in this case, an acetic acid. It's a weak acid. C double bond OH. Here we had C double bond H. The difference with an aldehyde is that we have first an oxygen and then the oxygen forming a bond with hydrogen. So it's called ethanoic acid because it's like 2C, we have two carbons, or the conventional name is acetic acid. Acetic is normally when we have two carbons, and you can read a file on Moodle that I uploaded before that explains this further, like this conventional name, if you are interested in it. So that you, but if you name it in the exam ethanoic acid, it's also okay. It's approved, but you just see acetic acid more often, and we always like see it everywhere, even in the supermarket. If we read it, for example, we read acetic acid, not ethanoic acid. So it's good to know this nomenclature as well, this name. Now, when we have, let's say, a mixture, so you have two chains. Let's say you have two carboxylic acids. In one carboxylic acid, the H is replaced with the other carboxylic acid, and in the other carboxylic acid, the OH is just replaced with the second carboxylic acid. So you have, let's say, this one and the second one, as if you had already two different acids. Let's say this is the first carboxylic acid, which was already bonding to like hydrogen here. This is the second carboxylic acid, which already had an OH. So this lost an OH, this lost an H, water molecule was formed, and the other two carboxylic acid were kind of reacting together, right? In this case, we get an anhydride. It's called anhydride. And the name just comes from the original carboxylic acid that formed it. So in this case, it's an ethanoic acid anhydride. So it means it's formed from, this is an ethanoic acid because we have 1 and 2 carbons. This is an ethanoic acid, 1 and 2 carbons. They merged together and they gave us this ethanoic acid anhydride. Okay, so the functional group is when you see this C double bond O, but instead of H, you see another C double bond O. So two carbonyl group, 1, 2, and oxygen is in between them. And of course, this is not a side group, this is in the middle. All right, the good thing is in the exam, you can take these notes with you. So you don't have to memorize, but you have to know them so that you can locate them immediately. Now we have the ester. When you see the carboxylic acid, just replace the hydrogen with another radical so that this carboxyl group is now in the middle between two different radicals. Then we no longer a carboxylic acid, we have an ester. And the name of an ester ends with ate. So this is the termination. And it comes from the groups, the carboxylic acid that formed it. When we talk in detail about ester, it's a reaction between an alcohol and a carboxylic acid. So this is some group, alkyl group, that is bonded to the original carboxylic acid. In this case, it's a methyl because it's formed with one carbon. And the carboxylic acid is an ethanoic acid or acetic acid because it's formed with two carbons. It takes the name of the alcohol and the acetic acid. Here, methyl acetate. This is a methyl group. Okay, methyl, and this is an acetic group. So acetic acid. So it's a methyl acetate. It's just a mistake. Correct it if you want. And this is how you name an ester. So the end is 8. Okay, here also. This is a dimethyl ether because this is a methyl. This is a methyl, and it's two methyls, so you say dimethyl ether because of this structure. So some radical, like the alcohol, where the side chain, the H, was replaced by a full radical, and we got this functional group in the middle instead of being at the end. So we get an ether, and it's composed by two different methyl groups. So it's a dimethyl ether. Okay, and same here for the ester, also corrected. It's a methyl acetate because it was formed by an acetic acid. Now, the amide, instead of the oxygen, we have the nitrogen. I just explained that the oxygen and nitrogen are just two different electronegative elements, and they behave almost very closely. Yeah, so we often see some compounds having, for example, the nitrogen elements instead of the oxygen. The N belongs to the fifth group in the periodic table, and O belongs to the sixth group. So oxygen has two lone pairs and can bond with two different elements. Let's say one is H and the other is just this, whatever is here, all this. Nitrogen can bond with, has only one lone pair and can bond with three different, so H, H, and here is just the rest, so radical. So OH can be replaced with the NH2 to form a different class of organic compounds. In the case of amide, it's like the ester. You see the similarity. The ester has this carboxylic group, this one in the middle, and we have the radical 1, radical 2. For the amide, it's the same, but instead of oxygen, we have the nitrogen, we have radical 1, and we have a second radical here as well. So it's just that the oxygen is replaced with the nitrogen, and we have an amide then, and not an oxygen. But remember that we have here two radicals, so because the nitrogen again has only one lone pair, so here we have the C, double O, N, and then the nitrogen is just radical, and here we have another radical, some hydrocarbon chain, yeah, whatever, can be whatever here. So this, in this case, it's an amide. And lastly, we have the amine. Amine is when we have the amino group NH2 as a side chain, and the termination is the full amine word. In this case, we have methyl amine, can be ethyl amine, depends on the radical, we name it. So this is very easy, but this is called primary amine because it's bonding to a primary carbon. What's the difference between a primary carbon and, for example, secondary carbon, tertiary carbon? Let's see them here. So this is the amine. It's NH2 and it's just a radical. Primary means like it's bonding to one carbon atom. So it definitely should be at the end. Or like somewhere on the side, but not in the middle. When the nitrogen is between two different radicals, so bonding to two carbons, then in this case it's a secondary amine. And when it's in the middle of three different radicals, so it's not bonding to any hydrogen anymore. The full three hydrogen are replaced by three different radicals. It's a tertiary amine. So it just depends on the number of carbon chains that's bonding to. And when, remember that here we have a lone pair, because the amine normally is this, is like this, bonds with 1, 2, 3 different groups or hydrogen. When this breaks and connects to a new radical, so for example, it connects to H plus or connects to a radical plus that is cationic, so it has like lost one electron, it gives it one of its origin electron to bond to get this like stability. In this case, this lone pair is not existing anymore. It's just like making a bridge with a fourth radical, which is very unusual for a for a nitrogen normally to form four bonds. The full compound becomes a cation, and it forms an ionic bond with an anion, for example, chlorine. In this case, it's called a quaternary amine because it's like bonding to 4 different carbon groups. 1 R here, 2, 3, 4, but it has this plus because it cannot attract a balanced molecular chain because it has this. There should be something to break this lone pair so that one of its original electrons are credited to the 4th radical so that it balances its charges and becomes kind of neutral. So the whole compound becomes plus because it has a deficit of electron, because this radical had originally a deficit of electron, and to balance itself it just formed a 4th bond with this nitrogen element. So this is a quaternary amine. And the same here, when we talk about primary, secondary, tertiary carbon, it means just a carbon that is bonding to how many other carbon atoms. In this case, this carbon here is a primary because it's only bonding to one carbon, like the direct bond. The direct bond is formed with one carbon atom. This one is also a primary because it's only bonding to one carbon atom, which is this one. This one is a secondary carbon because it's bonding to two carbons. And this one is a tertiary carbon because it's bonding to 1, 2, and 3 carbon groups. So this is a side note because we are going to need it later on with when we explain the reaction schemes and the different compounds that they form. All right. So now I think we finished the groups. We only have one more, which is the nitrile. The nitrile is a compound where we can see the cyanide. Cyanide is carbon, triple bond, nitrogen. This functional group is called cyanide, and when it's bonding to some radical, it's like we have this nitrile group. In this case, we have 2 carbons, one group here, the methyl, and a second one that is part of the functional group cyanide. So the name will be ethane nitrile. Ethane because it's like two carbons. Yeah, so the name is ethane, and nitrile is just the group to which this compound belongs. So it's ethane nitrile, and it has another conventional name, acetonitrile, because it's like 2 carbons again. If you are interested, you can read it on the Moodle, the acet name. So acetonitrile is also a conventional name. And a third name is methyl cyanide. So this is a cyanide, and this is a methyl bonding to it to form this nitrile. But in this case, we don't stress on the class. So it's better to show the name of the class to know that it's a nitrile compound. So ethane nitrile or acetonitrile is a better name in my opinion, but you can also call it methyl cyanide, or you can see it somewhere in the, like over the internet, let's say. All right, now I will come back to the top where I can explain how to draw the different structures of the molecules. We can draw it in a very explicit way, which is called the full line bond formula, where we write all the carbons, all the H, and we draw the single bonds with 1 line or the double bonds with 2 lines and so on. We can have an abbreviated line bond formula where we just write the hydrogen, but we don't write the carbon. But when we have an intersection, it means we have a carbon. But this is not very common because carbon are much more important than hydrogen. So it's not really important to show them explicitly if we are not showing the carbon, because we know that the carbon can form 4 bonds. So we imagine this. We have a more common version, which is the skeletal formula, where the carbon and H both are implicit, so they are not written. Here we mean that this is a carbon, because when we see an intersection between two lines, it's a carbon. And of course, the carbon is bonding with 4 bonds normally. So here's 1, here is 2. So of course it has 1 hydrogen, 2 hydrogen, but we don't write them. So this is 1 hydrogen, this is 2. We just don't write them, we write it like this. Here we know that it's a CH2 group. When it's at the end, of course, it's a CH3 group now, because this is like 1 carbon, 1 bond, then 1, 2, 3. It's a CH3 group at the end. We don't write it. So this is all implicit. But when we have OH group, we write the H that is bonding to oxygen. The only implicit H are those bonding to carbon, because it's like we assume that when we have a carbon, if we don't explicitly write its bonds, then it's just hydrogen. If it's bonding, for example, here to an hydroxide group, we don't write O, we write OH. So O and H, we write the full bond here. We can write OH or O bond H, doesn't matter. And of course, it has 2 lone pairs. So that's the difference between an implicit H and an explicit H that it should be written. Okay, I need to clear. And then we have another structure, which is called the constitutional formula. And here we don't draw the bonds or the lines, we just like kind of compress them or condense them. So instead of writing C and drawing these 3H, we just write CH3. And we know that they are 3 different bonds. So we just write CH3 and then CH2, 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 CH3. And sometimes we just abbreviate the constitutional formula. Instead of repeating CH2 4 times, we just write CH2. And then we put the this number 4 to show that we have 4 times the CH2 group. We can have a mixing of styles. For example, we draw this in a line bond form, like we explicitly put all the 3 H's, and here we just put them condensed CH2, CH3 in the constitutional form, and here we just write the skeletal form, which doesn't explicitly show these carbons or the hydrogen, but we know that we have, for example, here a carbon and 2H, and here we have 1H, and here we have 1H, here we have 2H, here we have 2, and so on. So we know, but we don't write them. Okay. Yeah, we can have a mixing of styles, and all of them are okay, unless you are asked to draw in a specific structure. Everything you can write the way you want. Now, sometimes we just abbreviate with the letter R if we don't care about the hydrocarbon chain and we just want to stress on the functional group to specify that this is a specific group. For example, alcohol. I just said that the alcohol has the hydroxide group at the end. But in this case, we don't care about the rest. We just write R, which means radical. So we just abbreviate it like that, ROH, to say that this is an alcohol. So the same here. This is an amino acid. It has the amine group, and it has the carboxylic acid at the end. So it has this amino acid, 2 functional groups. And the rest is just, you see, it's like aromats and some things, rings, and we don't care, we just abbreviate with R. Now, more than one R is possible, of course, so it depends if we have, for example, an ester, as I said, or a ketone. In this case, this is a ketone. You remember the aldehyde has this double bond O and then H. When the H is replaced with another radical, then the carbonyl group is in the middle, so it's a ketone. And I told you this is called a ketone in this case. The carbonyl group is called ketone. So this is a ketone, and you have 2 different radicals because the functional group is in the middle. So you have to distinguish this radical from this radical, and it's not considered one radical anymore because functional group is not an end group, is not at the side of the chain. Okay, here this is just conventional. If we want to indicate the 3D geometrical structure of the molecule, when we write it like this, with a kind of a solid line with edges like a triangle, it means it's pointing out of the screen towards us. So imagine that this is the plane. The CH represents the plane of the screen. The iodine and the bromine in this case are coming out of the screen towards us, and the chlorine is coming out of the screen but towards the back. So we represent it with pointed lines, with dotted line, okay? This is just to show that this molecule has a 3D shape. So let's take some examples of, also we can practice together. So the acetic acid, we can draw it like this with a full line bond structure, or with a skeletal form. You see, when we have an intersection, it means we have a C, but we don't write it explicitly, and then double bond O. And then we have the OH here. We write them explicitly, of course, but this one we don't write it, but it means we have CH3, but we don't write it. And this one also we don't write it. And this is a skeletal form. We have the constitutional form where we just contract them and we don't show the double bond anymore. But we can also write it like this, but want to stress that there is a double bond in this compound, so we can write it like this to show. So we contract everything else, but we want to put the double bond in contrast, so we write it like this, and then just OH. We can have a mixed style, so we just contract it here in a constitutional way, and here we show it explicitly. So it depends. This is called a mixed style. Now let's see some other examples. For example, the acetone. Remember the ketone. It's C double bond O in the middle. When we have one radical, two radical. Let's write them. So this is a full line bond formula, C double bond O, and then we have CH3, CH3. If we want to write the skeletal formula, we can write 3 points. So let's say one carbon represents a point, then carbon group, I mean. We don't care about the H. So this is the C structure, and then double bond O. So we will get this formula. Mixed style, you just, let's say, contract those. CH3, you write CH3 instead of drawing the full bonds. So this is the CH3, you write it and also write it, but you want to show explicitly the double bond O. Or the constitutional formula is CH3, C double bond O, CH3. Just write it like as if you're writing a name. Okay, this is interesting. It's called tert butanol. By the way, red represents an oxygen. So this is a carbon group, 1, 2, 3, 4. We have 4 carbon groups, but how are they bonded? We have this one in the middle, bonding to 1, 2, 3. So we have a tertiary carbon. Remember, I just explained this. When a carbon is bonding to 3 different carbon groups, it's a tertiary carbon. And we can call it, we can consider that the longest line is the main chain. So it characterizes the group of this compound. So the longest chain is 1, 2, 3, which means a propanol. Yeah, the functional group is OH. And it's made of 1, 2, 3 carbon groups, so it's a propanol. And there is one methyl group, CH3, connected to this propanol on the second carbon. So it's called a tert butanol. No, it's called methyl propanol. You can call it methyl propanol. Or actually 2-methyl propanol if you want to stress that it's on the second carbon. But you can also call it tert butanol, which means you consider that it's a butanol because it's made of 4 carbons, and instead of being like this, like 1, 2, 3, 4, and here OH, like you have 1 carbon, 2, 3, 4, you know, butanol. This OH, this side group now is here, connected to the second carbon, and the alcohol is also connected to the second carbon. So tert means that the alcohol, the functional group, is bonding to a tertiary carbon that is connected to 3 different carbons. So it's connected to this, and to this, because this one is no longer here, it's here. So you see, this is the carbon that we are talking about. It's connected to 1 carbon, 2 carbon, 3 carbons, and the functional group of the alcohol is actually bonded to this tertiary carbon. That's why it's called, like the other name of the methyl, you can call it methyl propanol, of course. This is the methyl, and this is the propanol. This is the methyl. Or you can call it tert butanol. So you consider that it's made of 4 different carbons, so it's butanol, and tert because the ol, or the OH group, is connected to a tertiary carbon. So this is what it means. Now, if you want to write the full line bond structure, it's easy. The skeletal formula, you replace the carbon with a point. You have 1 carbon, second carbon here, third carbon here, and then you have the OH. And you just connect the lines. So you get it like this: 1 carbon, 2, 3, 4, and you have the OH, and you connect the lines. Here it means we have a CH3 and so on. So you don't have to write them explicitly. Okay, now the mixed style is known, constitutional formula is known. Let's do a second example. Here we have the ene. Remember, we just talked about the classes. When we have a double bond, it's an alkene with E. So we have 1, 2, 3, 4 carbons, so it's a butene. And 2 means that the double bond is on the second carbon and not on the first. If the double bond was here, we will have, in this case, 1 butene, because we 1, 2, 3, 4. If it was here, we also count from left to right, 1, 2, 3, 4, it's 1 butene. But because the bond is here, then it's 2 butene. We take the lower number always. So this is a 2-butene. We call it sometimes trans-butene, and I will explain it when I got to the isomers at the end. So we can write it like this: explicit formula, full line bond formula, or skeletal formula. You write it with the points. We have 1 second carbon, we have double bond here, third carbon, fourth carbon, and just connect the lines. You get this butene. Constitutional formula, you have to put the double bond explicitly, and the rest you just condense them, compress all the, so you don't write the bonds, you just write CH3, CH, and so on. You can have a mixed style, of course. Now the glycine is an amino acid. We have the amine group. So blue is nitrogen and red is oxygen. We have the carboxylic acid, C double O, double bond O, OH. This is the carboxylic acid, the carboxyl group. And we have an amine, so it's an amino acid. We want to write the formula. Again, point for the C, connect them. Then we have here, sorry, this is not a C, this is an OH. This is the bond O. And we have NH2. You can write H2 like this, or yeah. So this is the skeletal formula. You have to write the H explicitly here. So either you write NH2 or you just draw 2H, but you have to write it. You can't just write the N and drop the H, because the H is only implicit when we have a carbon. but not when we have, by the way, this is wrong. I'll repeat it. We have a C, we have another C. They are connected. Then we have here OH, and this C is connected to the NH2. So now it's right. Okay, and here we have double bond O. Here you don't have to write the H's, but here you have to write the H's, and here as well, because they are not connected to carbon. So this is the skeletal formula. Okay. Constitution is easy. I don't have to repeat it. Now we explained this. Now we need to get to the isomers. So what does isomer mean? Isomer is when we have the same number of carbon, hydrogen, nitrogen, oxygen, whatever, the same number of elements in the compound, but they are different elements. So they are not the same. And they can be different in several criteria. And now we will see which criteria can differentiate them. So if you see this one and this one, if you count the total number of carbons, they are the same, 4. So the structural formula is like this one, the condensed one. For example, when you write CH4 or C2H6 or, this is called the structural formula. It's the same, but geometrical wise, so if you consider the geometry of the molecule, it's different. So both are C4H10, but they have different names, they have different structures, and the most important, they have different properties. So the boiling point, for example, of this molecule, although they have the same number of carbon and hydrogen, so similar in their composition, but not in their geometry or structure, and this influences their properties. The boiling point is very different. This boils at a much lower degree than this one. So when the structure is completely different, so here we have a chain composed of 1, 2, 3, 4 carbon groups. Here we have a chain composed of 1, 2, 3 carbon groups, the longest chain, and just a methyl attached to it, bonded to it. So the constitution is different. So in this case, we have a constitutional isomer, and this is very easy to detect. It's very easy because they are just different in their constitution. They just have in common the total number of elements. Other than this, they are not similar in any way. They even belong to different groups. This is a propane, this is a butane. Now, of course, sometimes we call it isobutane just to say that this can become a butane because it has 4 different carbon groups, but it's an isomer of the original butane where the main chain is actually composed of 4 carbons and not of 3. So it's different, completely different groups. One is propane, one is butane. We can have the same identical molecule, but the 3D structure is different. And this is one example. Here we say it's a conformation isomer. Conformation is about let's say the physical shape or the form of the molecule. The structure is the same. We have the same group, the same line structure and everything, but only in a 3D wise, if we want to see where this H is pointing and this H is pointing, for example, the molecules can be different. So if you consider this one, let's imagine that we are looking at this molecule from this side. What would you see? You see a hydrogen pointing to the back of the screen, so dotted line, and this one, let's say, in pointing towards us, let's say. Can you imagine what I'm talking about? So this is like in different planes. Now, if you rotate this so that this one also points to the back, at some point, all the other also, these two will also rotate. They will be aligned. So if you look from here, you will not see this group anymore because they are fully aligned with this molecule. So this is a side view. You can see it originally like this. These are the group in the back. The second C is just hidden behind the front one. If you turn it, they will fully align and give us this structure. So this is fully aligned behind it. You get a completely different compound. So this is one molecule, this is a second molecule. They are isomers. They are the same in their structure and their formula and their number of atoms, but they are just kind of rotated against each other. When the only difference is their rotation, so if you can rotate them along the axis in between them and you get the same molecule, it's called conformation isomer. So the only difference is the direction where they are pointing, and that this difference can be fixed by just rotating this, rotating them along the main axis, which is this one here. Now, another type of isomers is called an enantiomer, and here you have a mirror image. But this mirror image, you know, when you have a mirror image in a plane, in one plane, not in 3D, if you fold it, so if you fold this on top of this, you get the same structure again. So imagine that this is in one plane. If you fold it, you get the Cl here, the iodine here, the H here, the bromine here. So you get this like this exactly. But when you have it in 3D, this will not be the case if it's like this. So it's called asymmetric. It's a mirror image. But the difference is this chlorine is pointing towards the back. If you rotate the molecule, the chlorine will be pointing towards us. So this molecule has the chlorine pointing towards the back, and the new molecule, if you rotate it, will have the chlorine on the right side, but pointing towards us. So it's not the identical molecule. So in this case, it's an enantiomer, we call it. You can see it better in this, visualize it better here. You see, this is pointing towards us, this is pointing towards the back. If you rotate it, you will have the chlorine pointing toward the front, and bromine and iodine will be pointing towards the back. So it's not the same molecule. And this happens normally when we have a chiral center. It can be a chiral carbon or a chiral axis, or a chiral means that it's bonding to 4 different elements or groups. For example, in this case, we have hydrogen, chlorine, bromine, iodine. They are 4 different atoms. They can also be 4 different groups. So it can be methane, ethane, something here, some acid, something else, some hydrogen. In this case, it's called chiral. And when we have a chiral center, most often we have this enantiomer because their 3D structure is like a mirror, but when you fold it, it will not give us the same molecule. Geometry will be different. So this is one example also. We have here a chiral carbon. It's an amino acid. This one. This is a chiral carbon. It's bonding to 1 amine group, 1 carboxyl group, 1 hydrogen, and the 4th is just a hydrocarbon chain, whatever. Methyl group, something else, whatever, we don't care. So it's called a chiral carbon. Now, if you look at the geometry, these are pointing towards the back and radical pointing towards the front. You have some other molecule, which is exactly the mirror of this one. but it's not the same molecule. It's an enantiomer. It's an isomer. So it's a mirror, but if you rotate it or if you fold it, it will not give the same molecule. It will give like the inverse. So the radical here will be pointing towards the back. The hydrogen and amine group will be pointing towards us if you fold it, if you can imagine what I'm saying. So in this case, these are enantiomer. You can also have, one moment, yeah. In the enantiomer, you can have a chiral axis and a chiral plane. So not only the chiral center does not only have to be a carbon atom, it can be an axis or a plane. This is a plane, chiral plane. It's bonding towards chlorine, here towards bromine, in here to a different molecule formed by 1, 2, 3, 4, some ring. So in 3D, this is a plane and connected to 4 different molecule in the geometrical space. This is pointing towards us, this is pointing towards the back, this is to the top. So this is the plane. This is the plane here. It's not an axis, it's a full plane. So here without the bromine. And you have connected to different elements or groups. So it's a chiral plane. And you can have an enantiomer for this molecule if you have the mirror image for it. Okay. Why it should be different elements? Because if you have the same, so if you have here, let's say hydrogen, let's say all of them are hydrogen, the same, and you turn it, you will get, for example, hydrogen pointing towards us, and here hydrogen pointing towards us, and here towards the back. If you rotate it in the space, you will get again this molecule because it's hydrogen. But the difference here is that they are completely different elements, and when one is pointing towards the back and pointing towards the front, no matter how you rotate it, you will not get this molecule again, because you have to consider the same elements. So if iodine is like this, you should get an iodine and like this. So here you care about the element and its position. So if you have not a chiral carbon, you have a chance that they will align with each other when you rotate them once, twice, or 3 times, let's say, in the space. So when you have a chiral carbon, or a chiral plane, or a chiral axis in this case, this is a chiral axis also considered. This is an axis. You have a bromine, you have an hydroxide, you have a carboxyl group, and you have a carboxyl group also. So this is an axis in space. If you have a mirror image, then if you fold it, it will not give you the same molecule. So this is an isomer or an enantiomer. And the 4th type is a diastereomer. And here it happens when we have the cis. This is called a cis position, and this is called a trans position. The cis position is when both are from the same side of the main axis of the chain, and the trans position when they are from different sides of the main axis of the chain. This is for, of course, here we have some radicals. So the carboxylic group, it's not the hydrogen. Otherwise, if they are all hydrogen, it's the same molecule. But we have some radical. Here, the functional group are towards from the same side of the chain, and here they are from different side. When we have this shape, it's called trans. When we have this shape, it's called cis. And if you remember, when we were talking about the names, yep, we said trans. We can call it transbutene, because this is the main axis, we have one methyl from one side of the main chain and the other from the second side. So this is transbutene. Now, if this methyl group was like this methyl group was like this, then we will have a cis-butene. Okay, so it's called transbutene or cis-butene, but the systematic name is 2-butene because, like as I said, the double bond is on the second carbon and not here. If it was here, you cannot have a cis-butene or transbutene anyway, because you need a axis in the middle and some two radicals pointing from each side of the main axis or from the same side of the main axis. All right, so to conclude, we will just see the summarized slide of the isomers again. Yeah. The isomer tree. So this is an important question that comes in the exam, and how to know if two molecules are an isomer or not. If they have the same number of, let's say, the same formula, so same number of elements, of carbon, of hydrogen, nitrogen, everything is the same, then they are most probably isomers. Otherwise, of course, it's not isomer. For example, this here we have only 4 hydrogen, 1 carbon. Here we have 2 carbon and 6 hydrogen. Automatically, it's a completely different molecule, not an isomer. So if yes, then we have to proceed with these questions. Does it have the same atom sequence? If no, like in this case, we have here propane and then something connected to a methyl group, and here we have the main chain as a butane, so it's just a constitutional isomer. So the only similar thing is the number of total elements and total atoms, but the groups are completely different. If yes, then we have some stereoisomer. All of them are called stereoisomer. But in the stereoisomer, we can have conformation isomer, we can have enantiomer or diastereomer. If they have a mirror image and most probably a chiral center, then it's an enantiomer. If not, so they don't have a mirror image, but if we look closely and kind of rotate them along the bonds that are connecting them, we get the same structure and the identical molecule. In this case, they are just conformation isomer. So they are the same molecule, but only the direction where they are pointing in 3D are different, and it can be fixed by just rotating or sliding the bonds along each other. If not, then we most probably have a diastereomer, and in this case, we have the cis and the trans shape. The last slide is just to see when we have a conformation isomer also. We have this chair and boat shape, for example. If you look from this side, if you slide this, so you have these two. It's like a chair. You sit here and you put your legs here, let's say. If you slide this towards the bottom and you raise this up, you get this shape. And this is called a boat shape. So you can get from this to this by just rotating them, kind of rotating them along their bonds. So it's as if this is some axis and you are just rotating them along each other so that you can get the other molecule. You get exactly this molecule by just rotating and sliding them along the bond axis, the axis of their bonds. In this case, you have a conformation isomer. So you can also see it here. just check this. You pull this up, and those, like, you have a group in the back that where you don't see the C in the back, but you see the H's. Okay, you have one H here, and so on. But this is a CH2 group in the back that you don't see the C, but you see the H's in between the H's of the front molecule. And the same here. You have some CH2 in the back. If you rotate them, so if you rotate the H's, you get this identical, they will be aligned. So you align them behind each other. The same here. And the front one, you just pull it up so that it perfectly aligns with the back. And you also rotate it. So you rotate the H so that the H is perfectly aligned with the back. So this one here, you pull it like up, you know, and instead of being to the bottom, it will be to the back. And if you can do this by just sliding them, then you have a conformation isomer. So you can get from this shape to this shape just by rotating along the axis of the bonds and rotating the H as well along the carbon center. All right. So this is, you can also have this. So this is also a conformation isomer. You don't only have to rotate, like in this case, we are only rotating the H's, but it's also possible to not just rotate the H's, but also kind of slide the full carbon group in order to align it with another one so that we get the same molecule at the end. So in this case, we have a conformation isomer. Now we arrive to the end of our lecture. I hope you understand it better now. And as promised, I will also do some exercises, record them, and upload them to Moodle.